Okay, so we are at week 8, right after we're finished all our double linked lists, circular lists, linked lists, and now we're stepping back a little bit away from data structures and into recursion. And recursion is going to help us understand the merge sort, and there's some links in here that I posted for you to, visualize recursion. And I have some assignments in there that deal with recursion. So basically, let's just do some recursion. And this is Java. Okay, so file, new, recursion. Okay. So we do a little bit of this in, actually we don't do really this in the Java class, but I do this in the Python, I do this in the C++ class. So you guys remember what recursion is?
It's a function which calls itself.
Awesome, a function that calls itself. So, and there's some advantages and disadvantages to recursion. First of all, let's just do the thing that we could do with a loop. Let's do int I is equal to 0, I is less than 3, I plus plus, and then I do a system out println. I'm going to do a for I equals plus I, okay, and I run this thing. And you get, in the for loop, I is equal to 0, 1, 2. And I can do the same thing using a while loop, right? I can say int j equals 0 while j is less than 3, and then j plus plus, and then I'm going to put this stuff in there. All right, and this is my while loop, and it's a j, run it. All right, so here's your j, same thing, same but different. I can also do it with a do while loop if I wanted to. Okay, but let's just leave it at that. So you can do the same thing with a for loop, you can do it with a while loop. And generally speaking, by the way, if you can do something with iteration or with a loop, you should do it with a loop. And why is that? Because recursion, which is a function that calls itself repeatedly until some condition is met, if you take the CSIS28 or the CSIS12/12L class, which is the computer architecture, the assembly language, what happens every time we call a function? What happens in memory? It puts it in a stack, right? So the processor has a stack, which is where we're going to store every function that is being called, so that when it exits, we pop it off the stack. So every time we call a function, we push it on the stack. Every time we return from a function, we pop it off of the stack, right? But if you have a function which calls itself repeatedly too many times, you're going to fill up the stack and you're going to crash the program, right? That's the stack overflow, right? You can only call a function so many times, right? I might have a loop that, if I wanted to, I can make a loop repeat 1,000,000 times, no big deal, right? You can see it go really fast. But if I have a recursive thing, if I have a function that calls itself, you're not going to get anywhere near 1,000,000. You're probably going to get around 10,000, and then it'll be like, okay, that's it, program collapses. Okay, so that's the reason why, for a lot of these problems, if you could write it as a loop, you should write it as a loop. Okay, because you get into this stack overflow issues. The other issue is because of the nature of how functions are being called, how they're being pushed on the stack and they're being popped off the stack, the actual recursion is slower than iteration. So a recursive, repeating something a bunch of times using recursion is slower than iteration. Okay, and there's also limitations that, you know, you can only do recursion so many times. Okay, that being said, there are some problems that are easier solved with recursive calls than they are with iterative, right? And I'll show you some examples of this. And the main thing is the merge sort that you're going to see today. All right, so first thing is let me make a recursive function here. Okay, so I'm going to make a static function because public static void recurse, and that recursive function is going to take a number. Okay, and what I want to do is I want to basically simulate, you know, these results right here. I want to do the 0, 1, 2. Okay, so what I'm going to do is, let's say I'm going to call my function right here. I'm going to say recurse, and I'm going to send the number 0 initially. Okay, and the first thing that I'm going to do is I'm just going to add one of these system out print lines, and I'm going to show you that recurse num equals num. Okay, and then see what happens. So if I run this thing, what's going to happen? I call my function, I send the value of 0 here, right? I'm going to show you recurse num is equal to 0, and that's where it will stop. Okay, but that's not really recursion, right? So what I'm going to do next is I'm going to say, okay, well, call yourself with the value of num plus 1. Okay, what's going to happen now is as soon as it shows you the result here, which is what we saw in the bottom, right? Then it's going to call itself one more time, with this time with 0 plus 1, or the value of 1 for num. All right, it's going to show you the 1, then it's going to go and it's going to call itself again. This time it's going to be 1 plus 1, and it will actually go on forever until it crashes. All right, in fact, let's see it. Whoops. All right, and you can see that Java actually has these things that are built into it. Whoops. So let's see how many times it called itself before it crashed. Like I said, it's around less than 10,000 times. Okay, what was the error that I said we're going to get? Stack Overflow, right? So we pushed so many function calls on top of the stack that 8,371 later, Java said, okay, I had enough. Let me kill this whole thing for you. Okay, so we're not going to do this forever. We're only going to do it a certain number of times. And by the way, you know, you're not going to get a Stack Overflow error on a loop that happens 8,000 times. You can do it a lot more than that. Okay? So what I'm going to do is, in here, I'm going to say, okay, well, if my num is less than 2, I'm going to call the recursion. Okay? And now let's run this thing. And there's your result. 0, 1, 2. Make sense? So far? Okay. So if you already know this answer from another class, don't give it away. All of you might know it, but what's going to happen when I move the recurse num here? How are these results going to change when I move my system out print line from being here to being here? What is this going to show me? Yeah.
So then it'll flip, it'll say recursion num equals 2, recursion num equals 1,
Mm-hmm.
and then finally when it's
Yeah.
top, recursion
Right.
num equals 0.
What's your guess?
Well, I'm thinking it's gonna do all that before it prints. It's gonna do the first 2 lines before.
It's only going to do these 2 lines, you're saying?
What it's gonna do is gonna go through the whole thing and then print the last.
So you're saying it's only going to print this one? Okay, yeah. So this is, by the way, this is the game that I like to play with students who haven't seen recursion before. And that is basically, I can have a classroom full of students and I can ask people to guess. And if they haven't seen recursion before, they're going to guess the wrong thing every time, right? It's very fun to watch. Because recursion is hard to visualize. It's hard to wrap your mind around it. Some people will tell me, oh, well, it will only happen one time, this one. And somebody's going to say, well, it's not going to happen at all. It's going to be an error. Somebody's going to tell me, well, it's just the last one. And they're all good guesses, right? But what's going to happen is you're going to see it in reverse. Okay, so why does that happen? And that is the tricky part about recursion, trying to visualize this thing. So the way I would do this, and again, just to show you, I'm going to grab this recursion thing. I'm going to get it here, put it there, right? Run it again so you can see it. So it's 0, 1, 2. And then if I flipped it and I run it, then it's 2, 1, 0. So why is this happening? Let me draw some pictures in Excel to show you. So the original one makes sense, right? That one's easy enough. The next one here is, let me get Excel open. Okay. So I'm gonna get this thing. I'm going to paste it right in there. Okay. And then remember that what happens is I initially call this thing with recurse is equal to 0 right here. Oops. There you go, right? So I call this thing with recurse is equal to 0, which means that my value for num here, num is equal to 0. Num equals 0. Okay? So the next thing that's going to happen is I'm going to call this function now again. So what happens is num is equal to 0. Is 0 less than 2? Yes, it is. Now call yourself with 0 plus 1. So I literally grab this thing here. Let's see where I want to put it. Maybe there. Okay. And I am calling this function, or this method, again. But this time, I'm calling it with num is equal to 1. Alright? So I call it with num is equal to 1. Is 1 less than 2? Yes, it is. Let me reduce this a little bit so I can fit more stuff on the same page. And then as soon as I get this one done, I'm going to call this one more time. So I'm going to get this, copy it, paste it, I don't know, right here. And then this time I have another call with recurse is equal to 1 plus 1. So now the value of num is equal to 2. Right? Is 2 less than 2? No, it isn't. So at this point it stops calling itself. And this is the first time that we're going to do a system out print line. Right? So we're going to do a system out print line, and you're going to get to see recurse num is equal to 2. That's the first one. Right? As soon as we get to the end of this function, then we're going to go and return back to where I was called. So I'm going to go back right after I was called. Change the color. There you go. All right. So I get to the end of this function, and then I return back right after I was called. And what's the next thing that I'm going to do? As soon as that if is done, then we have a system on print line. So now I'm going to show you the next one, which is recurse num is equal to 1. That was the value of num when we called this function. And then as soon as we get to the end of this one, then I'm going to grab this thing and return back right after I was called to the original. And that is when I'm going to show you the original one, which is recurse num equals 0. Okay? And that's why this thing shows in reverse. So first we call it, then we call it, then we call it. Finally we get to the system out print line. We show the first one. We return to right after we were called. Show the next system out print line. Then we get to the end of the method. We return back from where we were called. Then we show the last one. Okay? So that is a recursion. Okay? And the idea is you have something happening until some final condition is met. You have some kind of a base condition. that is going to make this thing repeat. It's going to stop at some point, and then something is going to happen. Okay, so what is the actual application of this? Is the merge sort. Let's see if I have this stuff here. There's some links in there. Okay, so I'll let you read this at your own. So let me do look for merge sort. Merge sort. Okay, and here's the merge sort. So you have a list of numbers. You're going to split them in halves. Then you're going to split the halves into halves. Then you're going to split the halves into halves until there's no more halves left. Okay, when you're done splitting this thing into halves, then you're going to start assembling whatever's left in the correct order, right? The larger numbers go to the right in each of these. Okay, so this is basically as soon as we split this thing into halves, instead of doing a system out print line, we're going to have like some kind of a function call or method call that tells it, okay, now assemble this thing in the correct order. So then with every subsequent step, we bring back these different pieces into the correct order. So we get a list of things, we put it back into the correct order, right? And there are almost each of these sub-arrays are actually already sorted. So merging them in the correct order is actually a lot more efficient than any of the other sorts that we have learned up to this point. Okay, the efficiency of this is n log n, which is a lot better than n squared, which is what we had for all these other basic sorts, if you remember, right? All the basic sorts that we had a one loop inside of another loop. The outer loop happens about n times. The inner loop happens about n times. Of course, it could be like n divided by 2 or whatever, but it's approximately n for really, really big numbers. And so the loops themselves happen n squared times. Okay? Now, the efficiency of this was, we improved the efficiency of some of these things by not swapping so many things, right? The bubble sort, the initial bubble sort, we had a swap that was inside of the inner loop, right? So the swap happened n squared times. And swapping big objects is actually very slow, depending on how big the data, structure that you've created, however much space it occupies in memory. Then we said, okay, well, hold on, we're going to move the swap out of the inner loop, which was the bubble sort, and we're going to do the select sort, I think it was, right? The select sort was you move the swap out of the inner loop and into the outer loop, so now the swap doesn't happen n squared times. You still have the loop happen, both loops happen n squared times, but the swap happens just n times. And then the final step was, with the insert sort, was we're not going to swap at all. What we're going to do is we're going to pull the number, we're going to store it in some place, then we're going to move all the other numbers into that corresponding spot, and then when we find the correct spot where to insert that number, we're going to put it back into the correct place in the list. So by doing that, we eliminated the swap altogether, which saved us even further time. Still, it did not improve the actual efficiency of the loops, however many times they happen. They are going to happen n squared times, which is why all these basic sorts that we did, the bubble, the insert, and the select sorts, we can say that they happen n squared times. Not this one, though, okay? This one is n log n times. And you can read through the books about, through the book, the Carano and Lafleur, to see how we end up with this n log n. For more details, what else do I want to do? The next thing is, I just have a couple of assignments that deal with this recursion business. And that is assignment 10. Assignment 10, right? I have a couple of things for you to do with loops and with recursion. Okay, so the first one is, and there's figure 6.1 in the book. You can see what a triangular number is. But it's basically so there's a triangular numbers where you add the numbers. There's a factorial numbers when you multiply the numbers. So the factorial is basically if we're looking at the number 5, right? Right? If we're going to do 1 times 2 times 3 times 4 times 5, that ends up being 120. What is a triangular number? A triangular number is basically what we're going to do is we're going to do 1 plus 2 plus 3 plus 4 plus 5. So in one you're adding and the other one you're subtracting. And what I ask you to do is, yeah, multiplying. One is, so the factorial, let's say factorial of 5 is 5, or 1 times 2 times 3 times 4 times 5. The triangular numbers, or the summation, or the series, whatever you want to call them, is the 1 plus 2 plus 3 plus 4 plus 5. Okay, so what you're going to do is you're going to have to do it first. You're going to do this with loops. Okay? And then you're going to do it with a recursion. Okay? So it'll just be a good, little mental gymnastics for you to create all these different methods that, some of them are going to be iterative, the other ones are going to be recursive. Other things that you can do is, maybe write a program that's going to calculate, your retirement savings or something using recursion. How often you're going to accrue interest at what periods, right? And how much money you want to put into your savings or whatever in order for you to get to a certain goal or whatever. Those are some things that you could play around with and create using recursion and iteration. That's something for you to play with. So that's the first one. And the other one is merge sort using recursion. So there's a merge sort in this chapter. Okay? So get it to work. And merge sort is not, it's not the most trivial thing to do. I would not expect you actually to be able to come up with the merge sort algorithm on your own. I mean, you can play with it, try to do it. Good for you if you do, but it's not something that I expect of the students who are just learning data structures and, for you to come up with the merge sort algorithm. Same way that, later on we're going to have some other fancier sorts than this, the quick sort, the shell sort, right? Some of these algorithms are so fancy that they were, created by people who were basically the founding fathers of computer science who got their PhDs for coming up with these algorithms. And then it took like 50 years for other people to improve these algorithms and come up with like these fancy sorting algorithms that are built into like the Java language and stuff. Okay? So when we get to those, I also don't expect you to come up with them. Just play around, write it out so that you can see how it works and get your hands dirty with it, and that's it. What I'm going to ask you to do is the first part for the merge sort is just get it to work as is, right, in the original order, and then the second part is get it to sort in descending order. So the original merge sort sorts this thing in an ascending order, and the other one that you're supposed to modify a little bit and change it to become a descending order merge sort. Okay? Any questions? Okay, so this is all in LA4. These are, pages 304 through 319. He does a really good job explaining the merge sort, just like anything else that he does in that book. So I highly recommend it. Just read through it. And then if you want to look at some more practical applications for these different sorts, then look at the Corano textbook, which is not going to go into like much detail about the actual sorting algorithm, but more about the actual applications and stuff like that. Okay? So that is pretty much all I wanted to tell you for this week.
The page is wrong. It
Huh?
should be page 288.
Is it 288?
The listing is 6.6, it's page 288.
Page 288 through what? Well, are we 290? Well, let me add it in there. So this is or 288 through 290. I wonder if we maybe, if our pages are different, just in case. All right. So that's pretty much it. That's all I want to tell you as far as recursion is concerned. Nothing too complicated. Thinking recursively is hard because it's hard for you to jump in your mind a bunch of times and try to trace this thing as it's happening, but it's actually not necessary. You just have to kind of come up with a general idea of how it's supposed to work, and then kind of press the belief button that it's going to work, and then have a base case, which is going to happen when basically the system out print line happens in that recursive that I showed you. Right? That will be the base case, which happens whenever some final condition is no longer met. Right? So keep calling yourself until something happens, until something is no longer true, and then the base case is, okay, now let's go back to this thing, and then in the case of the merge sort, what we're going to do is we're going to put this separate split pieces into the correct order. So in here you would have a swap, or not a swap, but merge basically. And if you look at the example in the book, it's all broken down into little methods, and it's hard to understand. So you're gonna have to take your time going through that. Okay, and yeah, that's pretty much all I want to say about recursion. And what we're going to do is next time. Next time we're going to talk about more advanced sorting, the quick sort, the shell sort, right? So you can see, you kind of get your hands dirty with this. Maybe I should combine all of these into 1 week, but whatever. Okay, after that we'll talk about binary trees. What are binary trees? Binary trees are similar to linked lists, except the links are not one after the other. The links are kind of branching off. You can have multiple links from one, stemming from one. Then we're going to do hash tables. Hash tables are, they're actually built into the Java language. There's hash map, and these are actually used in encryption. Hashing is used in encryption. Heaps are basically a general form or yet another kind of a tree. And again, both of these are types of linked lists. Okay, so trees, heaps, linked lists, circular lists, double linked, double ended lists, they're all kinds of lists. Right? The heaps are basically a tree which allows you to have a certain insert algorithm that either the smallest and the largest, or the largest is all the way on the top, which allows you to basically throw a bunch of numbers into a heap, which is a type of a tree, and then as soon as you want to pick off the top things that's the top thing that's on the heap, you could use that to effectively sort, because the smallest thing or the largest thing is all the way on the top. You just feed a bunch of numbers into a heap, and then you just start taking them off one by one, and then they're going to be taken out in a correct sorted order. Okay, so there's a heap sort that is actually pretty much as efficient as the merge sort that I showed you. Then later on, I'm going to talk about graphs. What are graphs? Question?
So how's the heap different from the stack? If you're working both of them off the top?
Well, a stack.
Because you push and pop off the top on the stack. It sounds like you do the same on the heap.
No, okay, so the stack. Okay, so the question is, how is the heap different from a stack? The stack, things get pushed down and down and down and down, and it's like a stack of plates.
Right.
The heap is like a organizational chart. So it's not pushed straight down, it's kind of spread all over the roots of whatever you want to call it. Okay, so that is the heap. And then when we get to graphs, that's a completely different animal now, which is basically going to be, you've heard of what a graph is, right? You can have an XY graph. That's one type of a graph. Then later on, there's different examples of graphs, but you could have a map, and you have a bunch of cities, right, on the map, and you're trying to figure out what is the fastest way for me to travel from point A to point B on that map, right? And that kind of an algorithm is just done. It's the easiest way to do that is with arrays. We're going to be using arrays for that as well. And there's all kinds of different graphs in there. that I'm going to show you, and that's pretty much all there is. Then I'm thinking maybe I'm going to throw in maybe a hash map at some point, but we'll see. We'll see how the class is doing. So that's the plan. And then we'll talk about like what data structure to use what, and then the last couple of weeks are just catch up and turn in all the work you have. Okay? But I'll tell you that a lot of these, a lot of data structure classes, the way they're being taught, they kind of hang, they keep going and they kind of lose steam around the linked lists. So a lot of these, a lot of the data structure classes, especially at the community college level, they kind of stop at the linked lists. Like all this other extra stuff that I'm showing you in here is, gravy. So we'll go through all that. Okay? So that's all I have. Any questions? Okay? And so that's all for today. If you want to come over to the office, or if you want to stay here, you can work for another 45 minutes or whatever. That's fine with me. And I will post the video.